So here it is running on a Steam Deck, and as you can see, it works. It runs at full frame rate, although for any of the rest of the video, we're going to be looking at the PC performance instead, because I think it's sort of barely hitting the limits of what's possible on the Steam Deck. This is a video about voxel cone tracing. Voxel cone tracing is a method to do ambient occlusion and global illumination. Unlike ray tracing, voxel cone tracing simplifies the scene by voxelizing it into a series of MIP-mapped voxel textures. So you get both high-resolution voxelizations of the world as well as simplified ones. And then while doing tracing, you sample the fine-resolution voxels when you're close to the point you're sampling, and then bigger and bigger ones as you move out, which enables you to get a really good speed up in terms of total effect. Specifically, I've implemented a cascaded setup where you have a series of nested voxel scenes that are bigger and bigger with bigger and bigger voxels, each one twice as big as the previous. This lets you have a large scene without clear bounds. Otherwise, for the most common voxel cone tracing implementations, you have a fixed volume that you trace inside of. For updating the voxelization as the scene changes, the updates are staggered to the different cascades, so we start at the smallest one, then do the next one, and then go back to the smallest one, and then the one outside of the next one, and so on, in such a way that the closer you are to the origin, the more frequently it's updated, and as you go further out, it's updated more and more infrequently, which is generally okay, since voxelization is very coarse anyway, so small changes with very big voxels aren't going to result in any change, so you need a large time step for there to be any significant change anyway. To allow for a large open scene where the voxelization just works, every time that the voxel space origin is moved significantly, so that's maybe the camera location or a player character location, all of the voxel textures that where the origin shifted at least 2 voxels over are reprojected. So we take the voxel data in them, we shift it over, and then we fill in the edges using the voxelization that's outside of that one. For global illumination, I've aimed for a single bounce, so that means ostensibly light bounces off of some object in the environment, and then onto the triangle that we're rendering, and then to the camera. So that's opposed to direct light, which just goes from the light to the triangle to the camera. You can do multiple bounces with voxel cone tracing, but it adds costs and it tends to add a temporal element. So here's an overview of how it works. This video is not going to be a super thorough walkthrough of all steps of voxel cone tracing, but I've linked some resources that I looked at. I'm going to try to highlight what I thought were the most interesting points in getting this to work for me. So here's an overview of the pipeline. The first step is to take our scene geometry and turn it into voxels. And as I said, we do a couple of cascades per tick, not all of them, in a staggered way. I voxelize all of the static and the dynamic geometry the same every time. In theory, you could pre-voxelize the static one, never update it, and just redo the dynamics every step, which is maybe an optimization, and then you'd have to blend them together. But it's actually not so costly to do a voxelization, so it's quite okay. The next step is going to be to temporally blend the color and opacity of the voxels. This is done for 2 reasons, right? So voxels are discrete, and you get strong popping artifacts whenever something moves from one voxel to another. So by blending them, you smooth that out a lot, which removes artifacts. And the other thing is we have to do a very aggressive color quantization that I'll go into to make this possible, and not blending colors would also create visible artifacts. Then the skylight visibility of every voxel is computed, so can it see the sky or not? And then we temporally blend that light energy as well, since the skylight visibility has the same kind of popping artifacts otherwise as the voxelization itself does. And then finally, we can do cone tracing to get ambient occlusion and global illumination. So the 4 panels you can see here are, in the top one you can see the different voxel cascades. So the most nearby is white, and then yellow, magenta, cyan, red, as we go further and further out with bigger and bigger voxels. You can then see in the bottom left the voxelized color, so it's very strongly quantized. If you compare to the scene on the right, you can see how it's sort of inaccurate, but it's good enough. I don't really think that global illumination color needs to be very accurate. And doing it this way has some nice benefits. And in the top right, we have the skylight visibility that's been blended. So you can see how it's being lit from the top right? And then in the bottom is the final voxel cone trace result. Between the top right and the bottom right, the sun has moved a little bit. So voxelization, I think, most commonly relies on doing some geometry shader manipulation of the triangles and then rasterizing them with the hardware rasterizer into a 3D texture, one layer at a time. But I couldn't do that because SDL3 GPU that I'm using as the backend doesn't have the geometry shader. So it needs to be a compute shader-based voxelization. And ideally, you'd also, if you do the rasterization method, you'd also want a somewhat rare feature called conservative voxelization to avoid getting any holes in the voxelized representation. So currently this is a compute shader. It uses only uint atomics, so nothing special. And it requires you to have pre-computed triangle colors for every triangle that's being voxelized, but that could be done as a pre-processing step in the model definition. There are sort of two approaches you could take to voxelization shader. You could write it triangle-centric, so you take every triangle and you look at what voxels it intersects, and you stick that into the you stick its information into the right voxels in your data structure. You could also do like a voxel-centric strategy where you take every voxel, you intersect it against all triangles, and then you find its properties that way. Voxel-centric is nice because it makes blending easier, but it performs really badly if you have a lot of triangles, especially a lot of small triangles that aren't intersecting many voxels. Triangle-centric, on the other hand, performs really bad if you have really large triangles, and especially really differently sized triangles, because you end up with some invocations of the shader taking a long time and some going very quickly. So the strategy is going to be to do both to try and mitigate the weaknesses of them. So first, we per triangle voxelize small triangles. So any triangle that is small enough to intersect only two voxels in like an axis aligned, in like an AABB test, we know has to be inside of those two boxes and none other. So we can just directly voxelize that by writing its information to our voxel texture. For any larger triangle, we instead count how many of them fall into each 4x4x4 bin, and then write them to a buffer. Then we can do a prefix sum on the bin counts, and then go over the buffered large triangles again to store them back in a binned manner, where we have the starting offset and the number of triangles in every bin. And then when we have the bins, we can easily do a per bin or per voxel compute shader that reads all the triangles that it would intersect and write their data. And then it doesn't have to test against things that it couldn't possibly intersect with because we've already excluded them in the first step. And this ends up being quite effective. The voxelization texture is just one U32 per voxel, so 8 times 64 cubed voxel cascades. That's only a total of like 8 megabytes of information. Although you'd have to have another U32 if you wanted to store emissive light as well. I've only done diffuse color. So how is the information stored in one U32 for voxel? Well, there are 3 things we need. So we need the color of the voxel, and we need the normal of the voxel. Not truly the normal, but more like how much triangle is there in each facing direction. We might want a little bit of alpha as well. So for example, make the small triangles a little bit more transparent than the big ones. So a problem is that ideally with averaging colors, you'd want to, average the colors, which would mean something like you could have a floating point RGBA. You could store the total weight in A and then add them all up and average them in post. But you'd need to have floating point atomics because, of course, in the per triangle voxelization stage, many different invocations can want to write to the same voxel. So floating point atomics are not a guaranteed feature, and this would also use a lot more memory. So instead, I'd come up with a packing for all the information that can fit inside a single U32 and where we can average colors and normals using only atomic OR. The really simple realization here, right, is that if you encode a value as just a number of ones, then atomic OR is the same as a max operation. When we blend colors together, we probably want it to be the case that if you sort of blend all the colors, you end up with a middle gray. So to achieve that, each color is stored as a positive and as a negative shift from 0.5, right? So you can get it shifting downwards or shifting upwards. And then when you add it together, you get the real color value. This means that if you have something that is, no red and you blend it with a lot of red, you get medium red, which is the sort of effect we wanted to achieve with the blending. So then we use 2 positive and 2 negative bits of red and blue, and then 4 positive and 4 negative bits of green. That's just how the bit count worked out, but also green is the most perceptually important color, so it makes sense to have the most bits allocated to that. But possibly something like YCBCR encoding could be used instead, and maybe that would be even better. Then normal, we store just same kind of encoding, 4 bits for each normal direction. Alpha is also just 4 bits in the same kind of way. And like that, it's now no problem to just have a bunch of threads writing to the same voxel at the same time. They just all atomic OR into it. So what about the skylight visibility? To do global illumination, you need to figure out which voxels are hit by the light and store that light energy somehow. And there's a lot of ways that you can figure out which ones are hit by the light. One way is to use the shadow map of the light, if you have one, to test the visibility of voxels, much the same way that you would do with a regular shadow map test, and light the ones that are visible. Another way could be to take texels from the shadow map, figure out what voxel they go into, and then do the same kind of counting, prefix sum, binning, and then per voxel lighting, as we do with the voxelization. You could also ray trace the voxel representation, so you just, from each voxel, you trace the voxel structure towards the light. You could take your previous lit frame together with like a depth and normal buffer and stick the light from that frame into your voxel structure. Of course, then you'd get screen space dependent effects that are maybe undesirable. What I chose to do, which works for a skylight, is to do like a coherent sweep across all the voxel textures. If you think about a skylight direction, that corresponds to a certain like Bresenham line drawn through a pixel texture. So we can just pre-compute that line and then do it layer by layer through the entire texture in the sort of major light axis and figure out which voxels are lit, which ones are unlit. Now, a little bit of a drawback here is that we really have to do a MIP mapping stage at the end to relight the voxels in the big cascades that are also part of a small cascade. This is because the light accessibility is much higher when you have finer voxels, so you lose a lot of light if you don't do that for like long distance global illumination bounces, and that loses a lot of quality. So, blending between textures. So, ideally I wanted to have no temporal blending, but I think it's kind of, sort of in retrospect, I think it's kind of unavoidable for the voxel representation itself. Just because when you move from one voxel to another, like a triangle moves from one to another, it creates a sharp like flicker popping between one being fully occupied and the next being fully occupied. And you can't mitigate that just by like tweaking the triangle intersection. So the simplest way is really just to constantly blend between an old voxel state and the new one. And of course, right, at the same time we can blend the very quantized colors into nice ones that sort of change smoothly over time, so we don't get any color popping either in the global illumination. I'm just blending here with an exponential moving average, and it's calculated so that like the blending in the small voxel cascades happens much faster than in the big ones because they are updated more often. But the idea was to just pick a blending rate where it's as close as possible to just looking like the linear interpolation between the current states. If you wanted to store like a momentum of visibility and color for each texel and so on, then you could make a nicer blending. The light energy is also blended, right? And it's stored as a spherical harmonic, so it blends nicely. Yeah, a bit of a drawback here is that you can't easily have colored light. You might need a second. I mean, you might need like a separate per channel spherical harmonic or a second sort of light color value that you store to do that. So what do you do with the voxel representation when you have it? Well, as I said, you trace cones into it by taking samples at bigger and bigger cascades as you move farther and farther away. And a really efficient way of doing this is to line it up so that you only sample every cascade once. You can do a quadrilinear blend if you want to, but if you take one from each, it becomes very efficient, which sort of fits very nicely with doing a 60-degree cones and 6 cones and a hemisphere. But you can do smaller and bigger cones as well. You just either get a lot of overlap between the sort of conceptual circles that you're sampling, or you get a lot of one sample per voxel texture. You will have to do, one cascade and then the next cascade and blend between them, depending on exactly how big of a sampling radius you want. These 6 sampling cones are oriented, to sit on a line with the normal of the surface. And I've added a random rotation because if you don't, you tend to get artifacts that relate to these gaps between the cones. You could fix that by having more cones, but I think randomizing them and doing an edge preserving blur on the ambient occlusion and GI before you composite it is sort of a more straightforward approach and more efficient. To make sure that you can't see where one voxel cascade ends, as they sort of, they end in the distance, as we saw before. The contribution from each of these big circles is scaled based on the distance it is from the edge of its cascade, so that when it hits the edge of the cascade, it has no contribution. And by doing that, you smoothly fade them in as you get to sampling more and more core ones of them. I'm just doing a linear blend, but maybe a smooth step on that would look nicer. But it's necessary to not get any visible sharp cutoffs between the cascades. When you take the result of all these cones, you get the global illumination at that point. Whereas if you instead add up all of the opacity from every direction, you get a measure of the ambient occlusion at that point. And the ambient occlusion looks very nice. So, what about performance? As I said, it does run on the Steam Deck at about 60 FPS. I don't have a GPU trace from the Steam Deck because I'm not sure how to get one, but and I would say it's probably not realistic to do this on a Steam Deck, but maybe I'm wrong and it's possible to optimize it further. On my desktop GPU, it runs, I think, pretty well. It takes about 1 to 2 milliseconds to do all the voxelization updates, and about 1 to 3 added milliseconds for the voxel cone tracing itself. If we go over this graph in order, we can see we start out with a low pass that updates the target texture that we're going to voxelize into. So that's shifting it over if the cascade has moved and clearing out the cascades that we're going to voxelize into this step. Then we voxelize all of the meshes in the scene, and this is currently done just, looping over them in a stupid way. Then we have the prefix sum, which is very fast. Then we do the binning of the large triangles based on the prefix sum. And then we do the actual voxelization of all the large triangles, and you can see if you look at the core utilization graph at the top, that there's still some bins with a lot of triangles that delay the whole pass. Ideally, you really want to have some LOD system that makes the triangles a consistent size, sort of compatible with the size of the cascade, the coarseness of the cascade that you're currently voxelizing into. I don't have anything like that, so this is sort of a bad scenario. Then we have the light injection steps, so that's computing the skylight visibility and then the MIP mapping of all of the steps. So that's computing the skylight visibility and then MIP mapping, and then finally blending all the light energy. Then there's just regular shadow mapping and the depth prepass. You really want to have a depth prepass because the cone tracing is expensive. You don't want to do it more than once per pixel. And then we have rendering the geometry, and here you can clearly see that whenever there's any visible pixels take a lot of time to do because the cone tracing is expensive when compared to the ones that are invisible, right? But still, like 2 to 5 milliseconds is in the realm of possibility. I think especially if you only do the voxel AO, this is quite doable, and that's probably what I'm gonna do. I do want to use this, but I'm gonna stick to just voxel AO because it looks nice and it's substantially simpler and cheaper, right? The GI has some problems. So anyway, voxel cone tracing, very cool stuff. There's a lot of ways that you can go about it. Obviously, if you compare what I did here to the reference articles, then it's similar, but there's also some different choices made. It's a really interesting technique. I think you can make the GI look nicer than what I've managed to. In particular, right, the light injection strategy I think matters a lot, and then both having a good bilateral blur and perhaps a more cone traces per pixel to sort of capture the higher spatial frequency of light when compared to ambient occlusion would help a lot with making it look really nice. So here you can see the resulting screen. Now, here's the sponsor scene. You can see some moving geometry, and there's actually not one, not two, but three whole sponsor scenes rendered at the same time. So let's go back to the first one. There's a couple of debug modes we can use to visualize the voxelization. So here's a view of the cascades themselves. As you can see, we have a series of bigger and bigger voxels as you go further and further away, but the visual size on the screen is, constant because it's constant due to perspective, right? You can also see if we stand near the cube, how the nearby cascades are updated more frequently, whereas the faraway ones are updated more rarely. So there's sort of more. You can tell that the bigger faraway ones are updated at a lower frame rate. So if we go to the next, if we go to the next debug view, here's the voxel colors. Obviously, they're not super accurate compared to the colors in the actual model because of the very harsh encoding that we're doing. But I really don't think it's that important. And it does let us do the very well-performing atomic ore voxelization strategy. And finally, here's the light energy as seen from the skylight at each voxel. You can see how it moves around and how it has a bit of blending to it to avoid any clear popping artifacts. This is maybe a bit over blended. It's a question of tuning, but it is quite hard to get a really stable lit voxelization representation, and I think that's maybe one of the main problems with voxel GI. So if we look at the final scene again, right, you can see how the light reflects the colors of the banners to some extent on the walls. You can see a bit of moving reflected light and ambient occlusion around the moving geometry. You can see in the dark areas, you can see the ambient occlusion working. And you can also see how it's all, I don't know how this comes through in encoding, but how there is a bit of noise currently. This is a thing you can fix with an edge preserving blur or by just taking more voxel cone samples, but or even a temporally stabilized pass.